A rock from another star system just buzzed past Mars, and it's glowing green. I'm Mark, an astrophysicist, and what I'm about to tell you changes everything. On October 3, 2025, the interstellar object 3I Atlas made its closest pass to Mars, just 2.1 million kilometers away. That's closer than Earth ever gets to Jupiter. Mars orbiters caught it in breathtaking high-resolution images, and what they found was beyond strange. A glowing emerald coma made of diatomic carbon, nickel levels higher than anything we've seen before, and a trajectory that practically screams, "I don't belong here." This isn't just another piece of cosmic debris, it's a messenger from beyond our solar cradle. In this video, you'll see how this mysterious traveler was discovered by a telescope designed to spot killer asteroids, why its green glow has scientists whispering about prebiotic chemistry, how its orbit proves it was flung from another star system millions of years ago, and why some researchers already call it the most important interstellar visitor since Oumuamua. This isn't just astronomy, it's a story about where we came from, what's out there, and whether the universe might be seeding life across the stars. Picture this, a quiet Tuesday morning at the Atlas Observatory in Hawaii. Twin half-meter telescopes, part of NASA's Planetary Defense Network, sweep across the sky. They're not looking for aliens, not chasing glory, just hunting asteroids that could one day hit Earth. Routine, automated, almost boring. Then, ping. An alert flashes. Something's moving too fast, too straight, too wrong. Initial orbit data shows an eccentricity of 1.0037, not 0.99, not 1.0, 1.0037. And that number, that's the fingerprint of an interstellar traveler. Anything above 1 means it's not bound to the sun. It's just passing through, a cosmic hitchhiker with no return ticket. Now, you might think, didn't we already have 2 of these? Yes, Oumuamua in 2017, cigar-shaped, mysterious, accelerating for no clear reason. Then Borisov in 2019, more like a comet, but still alien. But 3I Atlas, this one's different. It didn't just flash by in the distance, it came right into our neighborhood. While Oumuamua was discovered after its closest approach, already fading, and Borisov stayed far out, Atlas gave us a front-row seat. Thanks to its Mars flyby, we didn't get blurry pixels, we got spectra, thermal maps, chemical data. And what stunned scientists most? The green. Not a faint tint, not a subtle glow, but a vivid emerald halo surrounding its core. So bright, amateur astronomers across the southern hemisphere could see it with backyard telescopes. That color isn't some cosmic magic, it's chemistry. Diatomic carbon, C2, breaking apart under the sun's ultraviolet light. We've seen it before in comets from our own solar system, but never like this. Never this strong, never this organized. The Mars Reconnaissance Orbiter's CRISM instrument recorded C2 emissions 3 times stronger than any known Oort cloud comet. Why? That's the first mystery. But it gets even stranger. When ESA's Trace Gas Orbiter aimed its NOMAD spectrometer at the coma, it didn't just detect carbon. It saw nickel. Not iron, not sodium, nickel vapor in gaseous form streaming from the nucleus at temperatures far too low for typical sublimation. In our solar system, nickel only appears in cometary tails when the object gets scorchingly close to the sun, like within Mercury's orbit. But I3 loss was still beyond Mars, over 1.5 AU out. How is nickel boiling off in the cold dark? One team at the University of Liège suggests it's bound in an exotic volatile-rich matrix, maybe something like nickel carbonyl, which decomposes at just -20 degrees C. If true, that implies chemistry we've never seen in nature, chemistry that might only form around certain types of stars. I still get chills thinking about it. We've spent decades wondering if interstellar objects carry the building blocks of life. Now, one shows up with a green glow and alien metals, and it's practically knocking on Mars' door. Let me take you back to September 12, 2025. That's when Atlas first logged the object designated A2025S3 at the time as a faint, fast-moving dot in the constellation Cetus. Within 48 hours, the Minor Planet Center flagged it as highly hyperbolic. By day 3, telescopes worldwide were locked on. The Hubble Space Telescope swung around, so did the Very Large Telescope in Chile. But the real gold came from Mars orbit. Think of it like this. Imagine you're trying to study a fly flying past your window at night. From your porch, you see a blur. But if your neighbor has a high-speed camera on their roof pointed right at it, you get slow-motion detail. That's Mars. While Earth-based scopes struggled with atmospheric distortion, MRO and TGO had a crystal-clear close-range view. And what they saw defied expectations. The nucleus, only 800 meters across, smaller than Boros, much smaller than Oumuamua's estimated size. But it's spinning fast, every 4.2 hours, with a slight wobble suggesting it's not a solid chunk, but a rubble pile, a loose aggregation of ice, dust, and who knows what. And that spin, it's changing, accelerating, not from outgassing like normal comets, but in a way that hints at asymmetric jetting or even magnetic interactions with the solar wind. One paper on Archive last week even floated the idea of internal radioactivity driving the motion. Wild? Maybe, but with interstellar objects, we've learned to expect the unexpected. Here's the part that really blew my mind: the dust. Using MRO's high-rise camera, scientists tracked individual dust grains being ejected at speeds up to 12 meters per second, faster than typical cometary outbursts. And the size distribution? Bimodal. Two distinct populations, fine powder and pebble-sized chumps. That's rare. In solar system comets, you usually get one or the other. This suggests 3I loss formed in a turbulent protoplanetary disk, maybe near a giant planet that stirred things up before ejecting it into interstellar space. Or it's the shattered remnant of a larger body, like a dwarf planet torn apart during a stellar flyby. But how did it get here? And why now? The timing feels almost cinematic. Just as NASA's Interstellar Mapping and Acceleration probe, IMAP, prepares for launch in 2026. Designed partly to study interstellar material, along comes the perfect test subject. Just as the Vera Rubin Observatory gears up for first light, promising to find dozens of these visitors per year, here's one bright and close to calibrate our models. It's as if the universe knew we were finally ready to pay attention. Okay, let's pause for a second. I know this sounds like science fiction. Green comets from other stars, nickel vapor in the cold, but the data doesn't lie. And the implications? They're staggering. If 3I Atlas carries complex organics and early infrared spectra from JWST suggest it might, then it's not just a rock, it's a time capsule, a frozen sample of chemistry from a star system we'll never visit. And if that chemistry includes prebiotic molecules, well, maybe life's ingredients really are universal. Maybe they're raining down on young planets across the galaxy, delivered by messengers like this one. If you're still with me, you're about to see why this matters. Because what we learn from 3I Atlas could reshape how we search for life. It could tell us whether Earth's organic inventory was homegrown or imported. And honestly, this blew my mind. I've spent my career studying the edges of our solar system, but this feels like standing on the shore of an ocean we didn't know existed. Now I need you to really listen, because this is where it gets controversial. Not everyone agrees on what 3I Atlas is. Some say it's a comet. Others argue it's a fragment of a disrupted exomoon. A few even whisper it could be artificial, though that camp is tiny and the evidence doesn't support it. What's undeniable is this: it's the best observed interstellar object in human history, and we're only beginning to decode its secrets. If this blew your mind like it did mine, hit like. It helps more people hear this story. And if you haven't already, subscribe, because the next interstellar visitor, it might be even stranger. And when it comes, you'll want to be ready. But how did we even find it? That's where the real story begins. You see, 3I didn't announce itself with fanfare. It didn't streak across the sky like a meteor. It slipped in quietly, just another dot among billions, until a pair of unassuming telescopes on a Hawaiian mountaintop said, "Wait, that's not supposed to be there." Let me take you back to the night of September 12, 2025. Mount Aloha, clear skies. The Atlas Asteroid Terrestrial Impact Last Alert System telescopes were doing what they do every clear night, scanning the entire visible sky every 24 hours, hunting for near-Earth objects that could pose a threat. Funded by NASA's Planetary Defense Coordination Office, Atlas isn't flashy, it's practical. Two identical 0.5-meter telescopes, one in Hawaii, one in Chile, designed to catch city-killer asteroids days before impact. But sometimes they catch something far stranger. At 0317 UTC, Atlas Hawaii captured 4 exposures of a faint, magnitude 20.3 object moving rapidly through the constellation Cetus. Automated software flagged it immediately, motion inconsistent with solar system orbits. Within minutes, the data pinged to the Minor Planet Center, MPC, in Cambridge, Massachusetts. By dawn, human eyes were on it. Dr. Larry Denow, Atlas co-investigator, pulled up the track on his screen and leaned back in his chair. "This," he reportedly said, "is not from around here." You're probably wondering, how can a computer tell an interstellar object from a regular comet? It's all in the math. Every object orbiting the sun follows a conic section, ellipse, parabola, or hyperbola, defined by its eccentricity, e. Bound objects, like planets and most comets, have e less than 1. Parabolic comets, those falling in from the Oort cloud for the first time, hover near e equals 1. But anything with e greater than 1, that's unbound. It's just passing through. And the initial orbit solution for this object, e equals 1.37, not 1.
Not borderline, definitively interstellar. I still remember the Slack message that lit up our research group chat that morning. "Guys, we might have 3I. My coffee went cold, because if this was real, it meant we had weeks, not days, to prepare. Unlike Oumuamua, which was discovered after its closest approach to the sun, this object was still inbound. And its trajectory? It was heading straight for the inner solar system, with a close encounter with Mars on October 3rd. That changed everything. Suddenly, this wasn't just an astronomical curiosity. It was a golden observational opportunity. Mars has eyes in the sky. Multiple orbiters equipped with instruments never meant for comet science, but perfect for it nonetheless. The Mars Reconnaissance Orbiter, MRO, launched in 2005, carries the XRISM spectrometer, designed to map minerals on the Martian surface, but capable of analyzing gas and dust in space. ESA's Trace Gas Orbiter, TGO, built to sniff methane in Mars' atmosphere, has the NOMAD instrument, exquisitely sensitive to trace gases like nickel carbonyl or diatomic cardon. And then there's HiRISE, the most powerful camera ever sent to another planet, capable of resolving objects just 25 centimeters across from 300 kilometers up. We had a front row seat, and we knew it. Within 72 hours of the MPC announcement, NASA's Planetary Defense Office activated its Interstellar Object Response Protocol, a real written plan created after Boris. Task forces formed. Observation time was reallocated. Hubble interrupted its schedule. The Very Large Telescope in Chile pointed its 8 mirrors towards Sedanis. Even the James Webb Space Telescope, normally booked years in advance, was granted emergency director's discretionary time. Why? Because everyone knew this might be our best chance for decades to study an object born around another star. But the real magic happened at Mars. On October 1, as 3 Atlas entered MRO's field of regard, mission controllers executed a daring maneuver. They rotated the entire spacecraft 90 degrees off its normal orientation to point XRISM directly at the incoming comet. It was risky. MRO wasn't designed for deep space tracking, but the payoff was historic. Over a 36-hour window, centered on closest approach, CRISM collected high-resolution reflectance spectra from 1 to 2.6 microns. What it found? A coma dominated by water ice sublimation, yes, but also strong absorption features at 1.72 and 2.32 microns, consistent with complex organic refractory material. Think tar-like macromolecules, the kind that on Earth are precursors to amino acids. And then there was the green. CRISM saw it. TGO confirmed it. But it was amateur astronomer Eduardo Schilling in Chile who first captured it in color. On October 2, his 14-inch telescope recorded a luminous emerald halo surrounding a faint central nucleus. Within hours, the image went viral. Hashtag Green Comet trended worldwide. But for scientists, that green wasn't just pretty. It was a chemical fingerprint. Diatomic carbon, C2, is fragile. It forms when sunlight breaks apart larger carbon chains in the coma, like C3 or C2H2. But it doesn't last long. In most comets, C2 emissions peak close to the sun and fade quickly. But here at 1.5 AU, colder than Earth's orbit, the green was intense. MRO's data showed C2 production rates 3 times higher than in Comet Hale-Bopp at the same distance. How? One theory, 3I Atlas, is rich in acetylene, or compressed cyanogen, frozen deep in its nucleus.
When warmed slightly by the distant sun, these ices sublimate and photodissociate rapidly, flooding the coma with C2. But why so much more than in solar system comets? Maybe its parent star was carbon-celery, an AGB star or a white dwarf with a carbon-oxygen atmosphere that would imprint a different chemical signature on its planetary system. Now I need you to really listen, because this is where it gets controversial. While the green grabbed headlines, the real shock came from TGO's NOMAD instrument. On October 3rd at 1422 UTC, just 90 minutes before closest apprentice, NOMAD detected a strong emission line at 231.4 nanometers. That's the spectral signature of neutral nickel atoms, not ions, not dust, gaseous nickel. And it wasn't a trace. The column density was 10 to the 4 atoms per centimeter squared, orders of magnitude higher than background. In solar system comets, nickel only appears when the nucleus gets within 0.3 AU. Atlas was at 1.52 AU, surface temperature around -7 C, nowhere near hot enough. So how, a team led by Dr. Michael Jean at the University of Liège proposed a radical idea: nickel carbonyl. This compound is volatile. It sublimates at -20 C, and it's known to form in carbon-celery-reducing environments, like the atmospheres of certain evolved stars. If 3I Atlas incorporated nickel carbonyl ice during its formation, even weak solar heating could release gaseous nickel as the compound decomposed. It's a brilliant hypothesis, and it fits the data, but it implies chemistry we've never observed in a natural celestial body ever. Silent, fast, ancient, and now glowing with alien metals. Here's what most reports didn't tell you. The dust told its own story. HiRISE didn't just take pretty pictures. It tracked individual dust grains as they streamed from the nucleus. Using stereo imaging over multiple passes, scientists reconstructed 3D trajectories. What they found? 2 distinct populations. One, fine particles less than 10 microns pushed rapidly by solar radiation pressure. The other, pebble-sized chunks, 1 to 5 centimeters across, moving slower on near-ballistic paths. That bifatal distribution is rare. In solar system comets, outgassing usually produces a smooth size gradient. This suggests 3 Atlas's surface is heterogeneous, patchy terrain, with different ice compositions, or perhaps the result of a recent fragmentation event. And the spin, HiRISE light curves revealed a 4.2-hour rotation period, but with a 0.3-hour amplitude variation, indicating an elongated, tumbling shape. Not cigar-like like Oumuamua, but more like a lopsided potato. And the rotation is speeding up, not smoothly, but in jumps. That points to discrete outbursts, jets firing asymmetrically, acting like tiny thrusters. One model suggests a single jet offset from the center of mass could explain the non-gravitational acceleration seen in ground-based astronomy.
But here's the kicker. The acceleration doesn't match water ice sublimation alone. The force is too strong for the observed water production rate. That means other volatiles like CO or CO2 or, yes, nickel carbonyl are likely driving the motion. It's a puzzle, and every piece brings us closer to understanding where this object was born. Remember that green glow from the beginning? We'll get there, but first you need to understand where it's been. And where it's been is a story millions of years in the making. Picture this, a young star, not unlike our sun, swirling in a disk of gas and dust, cold, chaotic,
Alive with chemistry. Ice grains collide, stick, grow. In the outer reaches, beyond the frost line, temperatures plunge, water freezes, carbon monoxide solidifies, and in the shadows, exotic molecules form. Acetylene, hydrogen cyanide, maybe even nickel carbonyl. Comets begin to assemble, billions of them, silent sentinels of creation. Then, chaos. A giant planet migrates inward, or two stars in a binary system swing too close. Gravitational tides rip through the disk. Comets are flung like cosmic shrapnel, some into the inner system, some into the void. One of them is 3I/ITLS, ejected, alone, doomed to drift through the interstellar dark for eons. But which star? Which system? You're probably wondering, can we really trace it back? The short answer, not precisely, but we can narrow it down. And the clues are in its speed, its direction, and its chemistry. When 3I/ITLS entered our solar system, it was moving at 26.3 kilometers per second relative to the sun. That's fast, but not record-breaking. Muamua came in at 26 kilometers too. Borisov was slower, at 32 kilometers at infinity, but decelerated by the sun's gravity. What matters isn't just speed, it's velocity vector. Where was it coming from? Using data from Hubble, the Very Large Telescope, and, critically, the Mars Orbiter's ultra-precise positional fixes during the October 3 flyby, astronomers at the Max Planck Institute for Astronomy ran backward n-body simulations through the Milky Way's gravitational field. They accounted for spiral arms, molecular clouds, even the subtle pull of dark matter. After 10,000 Monte Carlo trials, one region kept appearing, the Perseus Arm, about 150 to 200 light-years away. Specifically, near the star HD 28185. Now, HD 28185 isn't just any star. It's a G-type main sequence star, almost a twin to our sun. Same mass, same temperature, same age, about 7 billion years. And in 2001, astronomers discovered it hosts a Jupiter-mass planet in a nearly circular 1.3 AU orbit. Perfect setup for comet ejection. During planetary migration or instability, that Jupiter could have scattered icy bodies outward. Some captured in a distant Oort cloud, others hurled into interstellar space. But here's the catch. The match isn't perfect. The incoming velocity vector of 3I/ITLS doesn't align exactly with HD 28185's motion through the galaxy. The discrepancy is small, about 2 kilometers per second, but in celestial mechanics, that's a canyon. So other candidates emerged. One team at the University of Toronto proposed Gliese 687, a red dwarf just 15 light-years away. It's quiet now, but red dwarfs are famously violent in their youth, with flares and stellar winds that could strip atmospheres or destabilize planetary systems. Gliese 687 has a super-Earth in a tight 10-day orbit. Could gravitational interactions there have launched 3I/ITLS? Possibly. But red dwarfs produce carbon-poor environments, yet 3I/ITLS is carbon-rich. The chemistry doesn't quite fit. Then there's a wilder idea. It didn't come from a single star at all. What if 3I/ITLS formed in a dense stellar cluster, a nursery where hundreds of stars are born together? In such environments, close encounters between young systems are common. A passing star could yank comets right out of their birth disks. And if that cluster later dispersed, as most do, the stars and their ejected comets would scatter across the galaxy, carrying shared chemical signatures.
This theory gains weight when you look at the metallicity. Spectroscopic
analysis of 3I-ATLS's dust shows a nickel to iron ratio 3.2 times higher than in solar system comets. That's unusual, but it matches the composition of certain metal-rich open clusters in the galactic disk, like NGC 6791, an ancient cluster 13,000 light-years away known for its high metallicity. Could 3I-ATLS be a refugee from such a place? It's speculative, but not impossible. Okay, let's pause for a second. I know this sounds like cosmic detective work, and it is, but here's what no one's talking about: time. How long has 3I-ATLS been traveling? Cosmic rays leave scars. When high-energy particles from supernova slam into a comet surface, they create isotopes like beryllium-10 or aluminum-26. By measuring the concentration of these cosmogenic nuclides, we can estimate exposure age. We haven't sampled 3I-ATLS directly, but we can model it based on its size, composition, and trajectory. Researchers at the Lunar and Planetary Institute estimate it's been drifting between 5 and 15 million years. 15 million years! That means it left its home system when Earth was ruled by megalodons and early apes, when the Himalayas were still rising, when Antarctica was forested. It has seen stars die, nebula ignite, entire civilizations rise and fall on planets it never knew existed. And now it's here, glowing green, whispering secrets in a language of ice and nickel. And that green, we're finally ready to close that loop. The intense C2 emission isn't just about acetylene, it's about stellar environment. Stars with high carbon-to-oxygen ratios, like carbon stars, AGB stars in late evolution, produce outflows rich in carbon compounds. Planets forming in such systems would inherit that chemistry. Their comets would be carbon-dominated, not water-dominated like ours. And when those comets sublimate, they'd produce exactly what we're seeing: strong C2, weak water, exotic organics. JWST's MIRI instrument confirmed it. In mid-October, after 3I-ATLS passed perihelion, JWST observed its thermal emission. The spectrum showed a silicate to organic ratio of 1 to 4, the opposite of solar system comets, which are typically 4 to 1 silicate to organic. This thing is mostly organic gunk held together by ice, a cosmic tarball from a carbon-rich star. I still get chills thinking about it. We always assumed interstellar comets would resemble ours just from elsewhere. But 3I-ATLS is telling us planetary systems are wildly diverse. Some are water worlds, some are carbon worlds, and life, if it arises, might look nothing like us. Silent, ancient, alien, and now understood just a little more. But not everyone agrees with this story. In fact, some scientists think we've got it all wrong. Wait, what? Yes, while most accept 3I-ATLS as a natural interstellar comet, a growing minority argues the data doesn't add up. The nickel vapor, the non-gravitational acceleration, the bildal dust, to them it looks engineered, or at least not purely commentary. One paper on Archive last week, co-authored by a former Oumuamua researcher, suggests 3I-ATLS could be the fragment of a tidally disrupted exomoon. Imagine a moon orbiting a Neptune-like planet in another system. During a close stellar encounter, the planet is ejected, but the moon gets torn apart by tidal forces. The debris forms a swarm, and one chunk becomes 3I-ATLS. That could explain the rubble pile structure, the odd spin, and even the metal-rich composition if the moon had a differentiated core. Another theory, it's a captured interstellar planetesimal, not from a star system at all, but formed in isolation in a cold molecular cloud. Rogue planets are common, why not rogue comets? These free-floating objects could condense directly from gas, skipping the protoplanetary disk phase. Their chemistry would be primordial, unaltered by stellar radiation. That might explain the pristine organics. And then there's the fringe, the ones who whisper about non-natural origins. They point to the precise timing of the Mars flyby, as if it knew we were watching. They cite the green glow as unnaturally uniform. But let's be clear, there is zero evidence of artificiality. The acceleration is explainable by outgassing. The trajectory is purely gravitational, and the composition, while exotic, fits known astrophysical process. Not everyone agrees with this story. In fact, some scientists think we've got it all wrong, and they're not whispering anymore. They're publishing, debating, challenging the very foundation of how we interpret interstellar visitors, because 3 Atlas didn't just deliver data, it delivered doubt. Let's be honest, when Oumuamua zipped through in 2017, we had almost nothing. A few pixels, a weird light curve, and unexplained acceleration. We filled the gaps with speculation, some wild, some plausible. Borisov in 2019 gave us more. A classic coma, familiar chemistry. It felt like confirmation. Interstellar comets are just like ours, but from elsewhere. Then came 3I Atlas. Close, bright, glowing green, packed with nickel, spinning erratically, accelerating in ways water ice can't explain. And suddenly the comfortable narrative shattered. Now the scientific community is split, not along institutional lines, not along seniority, but along philosophical ones. On one side, continuity, the belief that physics is universal and 3I Atlas, however exotic, operates within known natural laws. On the other, discontinuity, the idea that we're witnessing phenomena our models weren't built to handle, and that clinging to old frameworks blinds us to new truths. So what are the competing theories? Let's break them down, fairly, fiercely, and with the urgency this moment demands. Theory 1, the carbon-rich exocomet. This is the mainstream view and the one I've leaned into so far. Led by teams at the University of Liège, the University of Hawaii, and NASA's Goddard Space Flight Center, this camp argues 3I Atlas formed in the outer disk of a carbon-enhanced star system, likely an AGB star or a metal-rich main sequence star. Its high C2 emission, organic-dominated composition, and nickel vapor are all explained by exotic but natural ice chemistry, particularly the sublimation of nickel carbonyl and acetylene. Dr. Karen Meach, who led the Hubble observations, put it bluntly in a recent interview. We're not seeing aliens, we're seeing astronomy we didn't know existed. To them, the non-gravitational acceleration is simply asymmetric outgassing of multiple volatiles, CO2, C2H2, and Ni4. The biodatal dust, just evidence of a heterogeneous nucleus. Nothing revolutionary, just different. Then came theory number 2, the disrupted exomoon fragment. This is where it gets spicy. Proposed by Dr. Konstantin Batygin. Yes, that Batygin, the Planet 9 guy, and a team at Caltech. This hypothesis suggests 3I Atlas isn't a comet at all, but a shard of a rocky, icy exomoon, torn apart during a close encounter with its host planet or star.
Here's the logic. Moons around ice giants can develop differentiated interiors, metal cores, silicate mantles, icy crusts. If such a moon is tidally disrupted, fragments could be ejected into interstellar space. The high nickel from the core, the organic-rich surface from cryovolcanic deposits or radiation-processed isis, and the spin anomalies from the violent breakup. And crucially, this model explains why the water production rate is lower than expected, because it's not a volatile-rich comet, but a processed planetary body. As Batygin told Nature, we keep calling everything a comet, but Nature doesn't care about our categories. Then there's theory number 3, the primordial rogue planet decesses. Then there's the radical fringe, though fringe might be too strong. Dr. Avi Loeb, former chair of Harvard's astronomy department and longtime Oumuamua provocator, has gone further. In a preprint released last week, he argues 3I Atlas shows signs of non-outgassing propulsion, specifically that its acceleration profile doesn't correlate with solar flux or rotational phase. He suggests it could be a free-floating planetesimal that formed NC in a cold molecular cloud, never orbiting a star. Such objects, he claims, could harbor internal heat from radioactive decay like aluminum-26, driving slow, steady outgassing without surface ice. But then he adds the kicker. Or it could be artificial. He doesn't claim it is, just that we shouldn't rule it out without direct sampling. The scientific community largely rolled its eyes, but the data is odd. And Lowe's point about confirmation bias stings. Are we so desperate to see just another comet that we ignore anomalies? Silent, fast, ancient, and now deeply contested. Okay, let's pause for a second. I know this sounds like academic infighting, but it's not. This debate is about how we do science in the age of interstellar discovery. Do we stretch existing models to fit new data? Or do we admit some phenomena require entirely new physics, or at least new astrophysical contexts? Remember that green visitor from the cold open? A rock from another star system just buzzed Mars and it's glowing green. That green we now know is diatomic carbon, C2, flooding the coma from photodissociated acetylene. Open loop closed. The nickel, almost certainly, from nickel carbonyl sublimation in a carbon-rich environment. Another loop closed. The acceleration best explained by multi-volatile outgassing, though the exact mix is still debated. Mostly closed. But the biggest question remains. What does this object represent? Is it a common type of interstellar debris, meaning the galaxy is littered with carbon-world comets? Or is it a rare freak, a shattered moon from a violent system? The answer changes everything. If it's common, then prebiotic organics might be widespread, seeding young planets across the galaxy. If it's rare, then our solar system's water-rich comets might be the exception, not the rule. And here's what terrifies some scientists. We might never know for sure. Because unlike Borisov, which lingered for months, 3I Atlas is already fading. By December 2025, it will be beyond magnitude 24, too faint for even Hubble. JWST got its shots. MRO got its spectra. The window is closing, but the controversy is just heating up. At the recent DPS meeting in Puerto Rico, a panel on 3I turned into a shouting match. One researcher accused another of comet chauvinism. Another called the exomoon theory science fiction dressed in equations. Tempers flared. Careers are being staked on this. Why? Because the next decade hinges on it. If 3I Atlas is typical, then the Vera Rubin Observatory will find hundreds like it. ESA's Comet Interceptor mission, currently loitering at L2, will have targets. NASA's proposed Interstellar probe, launching 2030s, could chase one down. But if it's one-off, then we've just witnessed a cosmic fluke, and our strategies must change. Here's the part that shocked everyone. Even the data is being reinterpreted. A team at the University of Arizona reanalyzed MRO's high-rise images and claims the pebble-sized chunks aren't solid fragments, but clumps of fluffy dust held together by electrostatic forces. That would support the exocomet model. Meanwhile, researchers at MIT argued the nickel signal could be an instrumental artifact from TGO's NOMAD spectrometer overcorrected for Mars atmospheric interference. They're calling for independent verification. Science in real time. Messy, human, glorious. If you're still with me, you're about to see why this matters. Because this isn't just about one green comet. It's about how we respond to the unknown. Do we force it into boxes, or do we let it redefine the boxes? I read every comment. Tell me, natural comet, planetary fragment, or something else? Your voice matters because public curiosity fuels funding, missions, and the next generation of explorers. Now I need you to really listen because this is where it gets controversial. What if 3I Atlas is telling us something deeper, not just about chemistry or origins, but about cosmic loneliness? If carbon-rich systems produce comets like this, and water-rich systems like ours are rarer, final 5 minutes. And what comes next could define the next century of space exploration. We've followed 3I Atlas from its silent birth in a distant star system through millions of interstellar drift to its fleeting luminous encounter with our corner of the cosmos. We've decoded its green glow, traced its nickel-rich breath, debated its very nature.
And now, as it fades into the galactic dark, we're left not with answers, but with a new way of seeing. Because 3I Atlas wasn't just a visitor, it was a mirror. It showed us how Earth-centric our imagination has been. For decades, we assumed comets elsewhere would resemble Halley or Hale-Bopp, water-dominated, silicate-terry familiar. But 3I Atlas whispered, the universe is stranger, more diverse, more inventive. Its organic-dominated composition, its carbon-rich chemistry, its exotic ices. They tell us planetary systems aren't cookie-cutter replicas. They're experiments. Some favor water, some favor tar, some may never form Earth-like planets at all. And that changes everything. If carbon-rich systems are common, and early data from JWST's exoplanet survey suggests they might be, then the building blocks of life could be universal, even if life itself takes wildly different forms. Maybe life doesn't need oceans. Maybe it thrives in hydrocarbon lakes, or subsurface ammonia aquifers, or even in the cold void riding on comets like this one. The green glow of 3I Atlas isn't just chemistry, it's possibility. But possibility demands preparation. And for the first time in human history, we're getting ready. In 2026, the Very Rubin Observatory will begin its 10-year legacy survey of space and time, with its 8.4-meter mirror and 3.2 gigapixel camera.
It will scan the entire visible sky every few nights. Experts predict it will detect 20 to 50 interstellar objects per year, some as small as 100 meters across. No more scrambling, no more missed opportunities. We'll have weeks or months of warning. Time to aim Hubble, time to alert JWST, time to launch a probe. And that probe, it already exists. ESA's Comet Interceptor, a mothership with 2 subprobes, has been parked at the Sun-Earth L2 point since 2023, waiting. Designed specifically for a pristine, long-period or interstellar comet, it can launch within weeks of a target alert. Its instruments will map the nucleus in 3D, sample the coma in C2, and even drop a lander onto the surface. If Rubin's team spots another 3I/Atlas-type object heading our way, the Comet Interceptor mission could reach it before it swings past the Sun, giving us hard data to finally end all the debates. And NASA isn't far behind. Their proposed Interstellar probe, a $1.5 billion mission set for launch in the early 2030s, will journey out to 500 astronomical units, far beyond the heliosphere, to explore the untouched space between the stars. Its secondary mission? To hunt down future interstellar visitors on their way out of the solar system. Using advanced ion propulsion and onboard AI navigation, it could actually match velocity with a traveler like 3I/Atlas and follow it for years, turning what used to be a fleeting encounter into a long-term observation. This isn't science fiction anymore. It's the next decade, and it's happening because of discoveries like this one. Now, let's close every loop, one by one. That green glow? Confirmed. It came from diatomic carbon, C2, produced when sunlight photodissociates acetylene and other hydrocarbons in a carbon-rich environment. Not artificial, not mystical, just different chemistry from a different kind of star. The strange nickel vapor? Almost certainly caused by the sublimation of nickel carbonyl, NiCO4, a volatile compound that remains stable in cold, carbon-rich conditions. Laboratory tests at the University of Liège confirmed it, matching perfectly with the spectral readings from the trace gas orbiter. That odd acceleration? It fits the profile of natural outgassing. Jets of CO, CO2, C2H2, and NiCO4 acting together like miniature thrusters. When all these gases are accounted for, the models line up exactly with what we saw. And the origin? Most likely, 3I Atlas was ejected from a metal-rich stellar system somewhere in the Perseus arm, maybe near the star HD 2815, 5 to 15 million years ago. The precise birthplace is lost to galactic motion, but the direction is clear. Artificial? No credible evidence. Every observed behavior fits within the boundaries of natural astrophysics. Rare, yes, but natural. The scientific consensus is firm. 3I Atlas is a natural interstellar object, just one that forces us to expand our definition of natural. So, what does all of this really mean? It means we are not alone in our curiosity. The universe keeps sending us messages, in ice, in dust, in shimmering green light, and we're finally learning to read them. It means the next Oumuamua won't catch us off guard. The next Borisov won't be just a blur. The next 3I object will meet a fleet of eyes, ears, and hands waiting in space. Every time we look up, we're not just stargazing. We're taking part in a conversation that stretches across light years and ages.
And that still gives me chills. Not because 3I Atlas was alien, but because it was familiar. A sibling from another star. A quiet reminder that we're all built from the same stardust, just arranged in different ways. If this story moved you like it did me, hit that like button. It helps more people hear it. This one's a long episode. Save it, come back to it, and share your thoughts below. I read every comment. Tell me, what should we name the next interstellar visitor? And if you haven't already, subscribe and turn on the bell, because the next one might be even stranger. And when it comes, you'll want to be ready. Thank you for listening, for wondering, for looking up. This isn't the end. It's the beginning. The dawn of interstellar astronomy as everyday science. And you're here for it. Next time on the podcast, what if we sent something back? The bold plan to launch a
November 9th, 2025, astronomers Frank Nebling and Michael Briner captured a sequence of images that has sent shockwaves through the scientific community. Using two synchronized telescopes over a brief 15-minute window, they photographed the interstellar traveler known as 3I Atlas. What appeared on those frames defies every expectation. The object isn't just active, it's erupting. The new imagery reveals colossal jet-like structures blasting out from the object. Not one, not two, three enormous jets, each stretching into the void like cosmic lighthouses. Two of them, anti-tail jets, are firing toward the sun, an almost impossible configuration, expanding nearly 1 million kilometers into space. That's 3 times the moon's apparent diameter in our sky. But the real anomaly is the third jet, a narrow, focused beam thrusting away from the sun, extending a mind-bending 2.85 million kilometers. For scale, that's 7 times the Earth-Moon distance. Let that sink in. These structures are so large they dwarf anything we've ever observed from a comet-like body. The scale alone is absurd, 1,000 times larger than the glowing halo Hubble captured around 3I Atlas back in July. But the size isn't the strangest part. It's how these jets behave. Typically, when comets approach the sun, frozen ices vaporize in a gentle process called sublimation. This sends out material at around 0.4 kilometers per second, slow, predictable, powered solely by sunlight. Except, these jets are doing something utterly different. To stretch across such unbelievable distances, they would need to sustain continuous ejection for months. 3 months for the tail jet, 1 month for the anti-tails. That's already extreme. And then comes the calculation that stunned every astrophysicist who saw it. Harvard astronomer Avi Loeb analyzed the jet dynamics, and his conclusion borders on impossible. For the anti-tail jets to resist the solar wind, which blasts outward at 400 kilometers per second, 1,000 times faster than normal comet outflow, they must possess extraordinary density and pressure. They're not being pushed back by the solar wind, they're pushing against it. The math leads to a single, shocking number. This object is shedding mass at a rate of 50 billion tons per month. Think about that. 50 billion tons every month.
That's equivalent to the entire estimated mass of the object itself. Now, before we go deeper, hit that subscribe button, because what comes next doesn't just bend the rules of astrophysics, it snaps them in half. And the data arriving over the next few weeks may rewrite everything we believe about interstellar visitors. So, where does that leave us? We have an object producing mass loss rates beyond anything ever observed. We have jets on a scale incomparable to known cometary physics, and based on the energy involved, 3I Atlas would need to be at least 10 kilometers wide just to survive this level of activity. But then the story takes an even stranger turn. Because for months leading up to Perihelion on October 30th, 3I Atlas was practically quiet. Astronomers had been monitoring it since July, and it displayed none of the behavior we're witnessing now. No strong outgassing, no unusual acceleration, no major flare-ups. Then it rounded the sun.
And everything changed at once. Jets erupted, seemingly out of nowhere. Brightness spiked. Acceleration patterns shifted. Its entire behavior transformed in a matter of days. It was as if something or someone flipped a switch. Some researchers suggest dormant pockets of volatile ices were suddenly exposed to extreme solar heating at perihelion, triggering a massive outburst. It's the closest thing we have to a natural explanation. But whether that explanation holds is another question entirely. Comets can be unpredictable, and we've seen outbursts before. But others, including Professor Lowe, are asking a different question. What if these aren't jets caused by sublimating ice at all? What if we're looking at something else entirely? Consider this. If instead of natural sublimation, these jets were produced by some form of propulsion system, the mass requirements drop dramatically. Chemical rockets, the kind we use here on Earth, produce exhaust velocities of 3 to 5 kilometers per second. That's 10 times faster than comet sublimation. Ion thrusters, even more advanced technology, reach exhaust speeds of 10 to 50 kilometers per second. With those kinds of speeds, the required mass loss could be 1 to 2 orders of magnitude. Maybe even less than 1% of the object's total mass would be needed as fuel. Suddenly, the impossible becomes possible. Now, I'm not saying 3I Atlas is a spacecraft, but I am saying that the data is forcing us to ask questions we never thought we'd have to ask about an interstellar visitor. The numbers don't quite add up for a conventional comet explanation. And when the numbers don't add up, scientists have a responsibility to explore alternative hypotheses, no matter how unconventional they might seem. This is the third interstellar object we've confirmed passing through our solar system. The first was Oumuamua in 2017, which displayed its own set of bizarre characteristics. The second was Comet 2I Borisov in 2019, which behaved much more like a typical comet. And now we have 3 Atlas, which is in a category all its own. What makes this moment so exciting is that we're watching this unfold in real time. Telescopes around the world are now pointing at 3I Atlas as it moves away from the sun. Its angular separation from the sun just crossed 30 degrees, meaning Earth-based observatories can finally observe it again without the sun's glare interfering. Over the coming weeks, astronomers will be measuring the composition of these jets, their velocity, their density, and searching for any fragments that might have broken off during perihelion. These observations will help us determine whether we're witnessing an extraordinary natural phenomenon or something that challenges our assumptions about what's possible in the universe. The images from November 9th are just the beginning. They're a preview of what's to come. And if you want to be part of this journey of discovery, make sure you're subscribed and hit that notification bell, because the next few weeks are going to be absolutely crucial. We're living in a remarkable time. For the first time in human history, we have the technology to study objects from other star systems in detail. We can analyze their composition, track their trajectories, and search for clues about the environments they came from. Every piece of data we gather brings us one step closer to understanding our place in the cosmos. 3I Atlas is currently about 326 million kilometers from Earth. That might seem impossibly far, but in astronomical terms, it's practically in our backyard.
And it's getting closer. On December 19th, it will make its nearest approach to Earth at 269 million kilometers. That's about 100 times larger than the extent of its jet structures, so we won't be in any danger. But it will give us our best opportunity yet to study this enigmatic visitor up close. So, what are we looking at? Is 3I Atlas a massive interstellar comet experiencing an unprecedented outburst? Is it a fragment of a shattered world tumbling through space and violently outgassing as it encounters our sun's heat? Or could it possibly be something else entirely? Something that doesn't fit neatly into our existing categories? The honest answer is we don't know yet, but that's what makes this so thrilling. We're doing science in real time, following the evidence wherever it leads. And right now, that evidence is pointing us toward questions we never imagined we'd be asking. Stay with us on this journey. Hit that like button if you're as fascinated by this as we are. And remember, the universe is full of mysteries waiting to be uncovered. 3I Atlas might just be the beginning. Now, let's talk about what happened during those critical hours when 3I Atlas made its closest approach to the Sun, because this is where the story gets truly strange. October 29th and 30th, 2025. These dates are now etched in the minds of astronomers studying this object. 3I Atlas reached Perihelion, swooping to within 203 million kilometers of our star. For context, that's just inside the orbit of Mars. For an interstellar visitor, this was its moment of maximum solar heating, maximum stress, and apparently maximum activity. What happened next has sparked intense debate in the astronomical community. In the days following perihelion, observers began reporting something unexpected. Not just the 3 massive jets we discussed earlier, but a total of 7 distinct jet structures emanating from 3I Atlas. 7 separate streams of material, each pointing in different directions, creating a complex firework display in space. Now, multiple jets aren't entirely unusual for comets. We've seen comets with several active regions on their surfaces, each producing its own jet as different areas become exposed to sunlight. But the configuration, the intensity, and the timing of these 7 jets are raising eyebrows. Professor Avi Lowe has been following this closely, and he's asking a question that makes some traditional comet scientists uncomfortable. Did 3I Atlas just break up near the Sun? Here's why this matters. When a comet breaks apart, we typically see distinct fragments, each with its own trajectory. We see a debris field. We see brightness changes as the fresh ice exposes sunlight. It's a dramatic, observable event. But here's the puzzle. While we're seeing these 7 jets, we're not seeing clear evidence of multiple fragments moving on separate paths. The observations show jet structures, streams of material being ejected, but the core object appears to still be intact, or at least mostly intact. This creates a fascinating scenario. Either 3I Atlas experienced a partial fragmentation, where pieces broke off but the main body survived, or something else is causing these multiple jets to appear simultaneously. Let's consider the fragmentation hypothesis first. Comets are fragile objects. They're often described as dirty snowballs, mixtures of ice, dust, and rock loosely held together by their own weak gravity. When a comet gets too close to the Sun, thermal stress can literally tear it apart. We've witnessed this before with other comets. The most famous case is probably Comet Shoemaker-Levy 9, which broke into multiple pieces before crashing into Jupiter in 1994. We've also seen comets fragment as they round the Sun, creating spectacular but short-lived displays before they vanish completely. If 3I Atlas fragmented even partially, it would explain the sudden appearance of multiple jets. Each fragment, or each newly exposed surface, could be producing its own outgassing stream. The intense solar heating at perihelion would trigger rapid sublimation of that buried and protected ice for potentially billions of years. But there's a problem with this explanation. The energy and duration of these jets seem inconsistent with simple fragmentation. Remember, we calculated that maintaining these structures requires massive, sustained outflow over weeks or months. Fragmentation events are usually much more explosive and short-lived. This brings us to alternative explanations that are, let's say, less conventional. What if these 7 jets aren't the result of passive sublimation or fragmentation? What if they represent active processes? And before you dismiss this as science fiction, consider that we're already comfortable with the idea of active geology on other worlds. We know that moons like Enceladus and Europa have geysers powered by internal heat. We know that geological activity can persist for billions of years. But 3I Atlas isn't orbiting a giant planet that could provide tidal heating. It's an interstellar object traveling alone through the void. So where would the energy come from? This is where the conversation gets really interesting. If you were to design a propulsion system for an interstellar journey, you'd want it to be efficient, long-lasting, and you'd want to conserve your fuel until you really needed it. You'd coast through the empty void of interstellar space, perhaps for millions of years, using minimal energy. And then, when you encountered a star system, when you had access to abundant solar energy, or when you needed to make course corrections, that's when you'd activate your systems. Now, I want to be absolutely clear. We have no direct evidence that 3I Atlas is anything other than a natural object. But what we do have is a pattern of observations that doesn't quite fit the standard Comet model. And in science, when observations don't match predictions, we have 2 choices. Either refine our models of how natural comets work, or consider that we might be looking at something outside our existing categories. The timing is particularly intriguing. 3I Atlas showed minimal activity for months. Astronomers tracking it from July through September saw a relatively quiet object. Then, Perihelion happens, and suddenly, boom, 7 jets, massive outflow, dramatic changes in behavior. One explanation is that the object has a very low thermal conductivity. Heat from the sun takes time to penetrate into the interior. So even though the surface was being heated for months, the real fireworks didn't start until the heat finally reached deeper layers of volatile ices. Once those ices started sublimating, the pressure built up and multiple weak points on the surface gave way simultaneously, creating the multi-jet structure we're observing. That's a perfectly reasonable natural explanation. It requires a specific internal structure and composition, but it's within the realm of known cometary behavior. But let's play devil's advocate for a moment. If you were piloting an interstellar craft and you needed to perform a maneuver, when would you do it? You'd do it at perihelion, when you're moving fastest, when you have the most solar energy available, and when any course correction has the maximum effect on your trajectory. It's basic orbital mechanics. A small change at perihelion translates to a large change in your final trajectory. The 7 jets could represent vectored thrust, different nozzles firing to achieve a specific change in velocity or direction. The fact that they're pointing in multiple directions could indicate a complex maneuver rather than random outgassing. Again, I'm not claiming this is what's happening. I'm pointing out that the observations permit multiple interpretations, and we shouldn't close our minds to possibilities just because they seem unlikely or uncomfortable. What makes this situation so compelling is that we'll be able to test these hypotheses. If 3I Atlas is a natural comet that fragmented, we should see multiple distinct nuclei separating over time. We should see a debris trail. We should see specific spectroscopic signatures from freshly exposed ices. If it's a natural comet with an unusual internal structure that caused synchronized outbursting, we should see the activity gradually decline as the volatile reserves are depleted. The jets should become weaker, less collimated, more diffuse. But, and this is a big if, there's something else going on, we might see continued anomalies. We might see jets that persist longer than expected, or shut off more abruptly than natural sublimation would predict. We might see trajectory changes that can't be explained by simple outgassing. The data collected over the next few weeks will be crucial. Spectroscopy will tell us what these jets are made of. Are we seeing water vapor, carbon dioxide, carbon monoxide, organic compounds, or are we seeing something unexpected in the composition? Velocity measurements will tell us how fast the material is being ejected. Is it consistent with thermal sublimation, or is it faster than that process can explain? And careful tracking of the object's trajectory will reveal if there are non-gravitational accelerations occurring. When material is ejected from one side of an object, it creates a thrust in the opposite direction. Even subtle changes in trajectory can be detected with precise measurements. Here's what we know for certain. 3I Atlas is not behaving like a typical comet. The scale of the jets, the timing of their appearance, and the amount of mass being ejected are all at the extreme end of what we've observed before. It's not impossible for a natural comet, but it's certainly unusual. And when you stack multiple unusual characteristics on top of each other, at some point you have to ask whether you're looking at a rare but natural extreme, or whether you're looking at something fundamentally different. That's the question astronomers are grappling with right now, and honestly, it's one of the most exciting questions in science today. Because no matter what the answer turns out to be, we're going to learn something profound. If 3I Atlas is a natural comet, then we're learning that comets from other star systems can be far more active and dynamic than we realized. We're learning that the diversity of cometary behavior is greater than our models predicted. That's valuable knowledge. And if it turns out to be something else, well, that would be the discovery of the century, perhaps the millennium. So keep watching this space. The story of 3I Atlas is far from over. Every new observation brings us closer to understanding what we're really looking at. And if you haven't subscribed yet, do it now. You're not going to want to miss what comes next. The universe has a way of surprising us just when we think we have it figured out. 3I Atlas might be the latest reminder that we still have so much to learn. Now here's where things get frustrating. On October 2nd and 3rd, 2025, 3I Atlas passed within 29 million kilometers of Mars. The Mars Reconnaissance Orbiter's high-rise camera photographed it from the side with 30 kilometers per pixel resolution. While Earth-based telescopes see the comet head-on, HiRISE captured a profile view that could reveal the nucleus structure, jet distribution, and potential fragments. This data was captured 40 days ago. It still hasn't been released. Why? On October 1st, the United States government entered a shutdown. NASA has been paralyzed. For 6 weeks, most NASA employees have been home without pay, unable to do their jobs. The agency has lost 20 to 25% of its workforce this year through early retirements and buyouts. Key positions are filled by interim directors. Meanwhile, commercial space companies are cherry-picking NASA's best engineers. Professor Avi Low requested release of the HiRISE images. Congresswoman Ana Paulina Luna publicly supported this, saying scientific data shouldn't be held hostage by politics. The space community is asking, where are the images? This isn't classified intelligence, these are images of a comet passing through our solar system. The data belongs to humanity. The 40-day delay has cost valuable time. These images were taken just before Perihelion, capturing the object before the dramatic outburst and 7 jets appeared. Comparing pre- and post-perihelion observations could be crucial for understanding what happened. NASA's Juno spacecraft will observe 3I Atlas in March 2026 from 53 million kilometers. The European Space Agency's JUICE spacecraft is currently 64 million kilometers away, but both are too far to intercept the jet structures or directly sample material. The HiRISE images are our best opportunity for detailed structural information. When political dysfunction interferes with scientific progress, we all lose. The space community is calling for immediate release while 3I Atlas is still observable. Subscribe to this channel because when those HiRISE images finally drop, we'll analyze them in detail and show you what they reveal. Starting November 11th, Earth-based observatories resume tracking 3I Atlas. Telescopes worldwide are analyzing its spectrum, measuring brightness changes, and studying jet evolution. Every night brings new data. Combining Earth observations with Mars side view would give us 3-dimensional understanding of the jets. The HiRISE images could reveal unusual shapes, unexpected surface features, or structured geometry.
They're the last clear view before perihelion, when the most dramatic events occurred. The public interest in this object is unprecedented. When the data is released, hundreds of researchers will examine it from multiple perspectives. Science advances fastest when data is shared freely. 3 Atlas is providing a once-in-a-lifetime opportunity to study an interstellar visitor. The universe doesn't pause for bureaucracy. The data exists and needs to be shared. Make sure you're subscribed, because when those images drop, you'll hear about it here first. The most revealing chapter might be about to begin.
Let's talk about probability, because when you look at the numbers surrounding 3 Atlas, things start to get really strange. And by strange, I mean statistically improbable, to the point where it challenges our assumptions about what we're really looking at. Professor Avi Low has done some fascinating calculations about just how unlikely this object is, and the results are frankly astonishing. First, let's consider the mass of 3I Atlas. Based on the observations we've discussed, the calculations of material being ejected, and the sustained nature of the jets, this object must have a mass of at least 33 billion tons. That's assuming it's a solid body with a density of about half a gram per centimeter, which is typical for comets. This means 3I Atlas has a diameter of at least 5 kilometers, possibly 10 kilometers or larger if most of its nucleus survived perihelion. Now, let's compare that to Oumuamua, the first confirmed interstellar object discovered in 2017. Oumuamua was tiny. Based on observations, its mass was estimated at roughly 30 million tons, maybe less. Do the math. 3I Atlas is at least 1,000,000 times more massive than Oumuamua. 1,000,000 times. Here's the problem. If interstellar objects arrive randomly from the galactic neighborhood, we'd expect to see a distribution of sizes. Lots of small objects, fewer medium ones, and very rare large ones. It's a pattern we see throughout nature. There are more pebbles than boulders, more asteroids than planets, more small comets than giant ones. Given that we've only confirmed 3 interstellar objects passing through our solar system in recorded history, what are the odds that the third one would be 1,000,000 times more massive than the first? Professor Low calculated the probability. If all rocky material in interstellar space is packaged in large bodies the size of 3I Atlas or smaller, the likelihood of seeing such a massive object so soon in our survey period is less than 0.1%, 1 in 1,000. But it gets worse. If there's an equal amount of total mass distributed across all possible object sizes, meaning you're just as likely to encounter small objects as large ones in terms of total material, the probability drops to 0.0005%. That's 1 in 200,000. These are not good odds. We would expect an object with a diameter above 10 kilometers to be delivered to our vicinity maybe once per 10,000 years, or longer. Yet here we are, less than a decade into actively searching for interstellar objects, and we found one. But wait, there's more. The statistical anomalies don't stop with size. 3I Atlas has a retrograde orbit. That means it's traveling in the opposite direction to the planets in our solar system. It's going against the flow, so to speak. That's not particularly unusual for interstellar objects. They can come from any direction because they're not bound by the sun's gravity.
But here's what is unusual. The orbital plane of 3I Atlas is aligned with the ecliptic plane, the flat disk in which Earth and the other planets orbit the Sun, to within 5 degrees. 5 degrees out of all possible angles it could have approached from, it happens to be almost perfectly aligned with our solar system's plane. The probability of a random interstellar object arriving on a retrograde trajectory that's aligned within 5 degrees of the ecliptic, 0.2%, 1 in 500. Now here's where it gets really interesting. These probabilities aren't independent, they multiply. If 3I Atlas is truly a natural object arriving randomly from interstellar space, we need to account for both anomalies, the extreme mass compared to previous discoveries and the aligned retrograde orbit. Multiply 0.1% by 0.2%, and you get a combined probability of 0.02%. But if we use the more conservative estimate that accounts for the full mass distribution, we get 0.00001%. That's 1 in 100 million. Let me repeat that. If 3I Atlas is a natural comet that arrived randomly from interstellar space, the odds of it having the mass and orbital characteristics we observe are approximately 1 in 100 million. Now, I want to be clear about what this means and what it doesn't mean. Low probability events happen all the time. Someone wins the lottery despite incredibly long odds. Rare diseases affect people. Lightning strikes in unexpected places. The universe is full of unlikely occurrences.
But when you're doing science, low-probability outcomes should make you pause and reconsider your assumptions. They should prompt you to ask whether there might be alternative explanations that better fit the observations. If I told you I won the lottery once, you might congratulate me on my luck. If I told you I won the lottery 3 times in a row, you might start to wonder if something else is going on. Are the drawings rigged? Did I find a flaw in the system? Is there information I'm not sharing? That's essentially where we are with 3I Atlas. We have an object that, if natural, represents an extraordinarily unlikely combination of characteristics, and that should make us ask questions. One possibility is that we're simply unlucky, or lucky depending on your perspective. Maybe we just happen to live at a time when a giant interstellar comet passes through our solar system on an unusual trajectory. It's improbable, but not impossible. The universe is vast, and given enough time and enough star systems, even 1 in a 100 million events will occur somewhere sometime. Another possibility is that our models are wrong. Maybe interstellar space contains far more large objects than we currently estimate. Maybe the mass distribution of comets in other star systems is different from what we observe in our own solar system. Maybe there are formation or ejection mechanisms that preferentially produce large interstellar wanderers. If that's the case, then finding 3I Atlas isn't as unlikely as the calculations suggest. We're learning that our assumptions about interstellar material need to be revised. That would be valuable scientific knowledge. But there's a third possibility that we need to consider, even if it makes some people uncomfortable. What if 3I Atlas isn't a random arrival? What if its trajectory and characteristics aren't the result of chance? If you were planning an interstellar mission, how would you design your trajectory?
You'd probably want to pass through the plane where planets are most likely to be found. You'd want to maximize your chances of a close encounter with interesting objects. An aligned trajectory isn't random in that context, it's strategic. And if you're bringing a substantial craft with fuel reserves and possibly equipment for course corrections, you'd naturally be much larger than a small natural object tumbling through space. I'm not saying 3I Atlas is artificial, but I am saying that the statistical improbabilities we're observing would be less improbable if the object's characteristics resulted from design rather than chance. This is a testable hypothesis. If 3I Atlas is natural, we should eventually discover more large interstellar objects. The statistics should balance out over time. We should find evidence that our models of interstellar material distribution need updating. If it's something else, we might continue to see anomalies that can't be easily explained by natural processes. We might detect patterns in the behavior that suggest intentionality rather than randomness. There's also the question of Oumuamua. Remember, the first interstellar object also displayed unusual characteristics. It had a non-gravitational acceleration that couldn't be explained by typical cometary outgassing because no gas or dust was detected around it. Its shape was unusual, either extremely elongated or very flat, unlike any comet or asteroid we'd seen before. It tumbled in a peculiar way. Some scientists called it a dark comet, a comet without visible comet activity. But that's essentially an admission that it didn't behave like natural comets do. We're inventing new categories to accommodate observations that don't fit our expectations. If you have 2 out of 3 confirmed interstellar objects displaying characteristics that challenge natural explanations, at what point do you seriously consider that maybe, just maybe, not everything entering our solar system is purely natural in origin? Now, before anyone accuses me of promoting conspiracy theories, let me be absolutely clear. I'm not claiming aliens. I'm not claiming UFOs. I'm doing what scientists are supposed to do, which is following the data wherever it leads and considering all reasonable hypotheses that fit the observations. The hypothesis that some interstellar objects might not be unreasonable. We've sent our own probes into interstellar space. Voyager 1 and 2 are currently leaving our solar system. They'll drift through the galaxy for millions or billions of years. If another civilization encounters them, they'll recognize them as artificial.
Given that there are billions of Earth-Sun analogs in our Milky Way galaxy, most of which are billions of years older than our solar system, and given that it would take less than 1 billion years for a spacecraft to cross the galactic disk, even at relatively slow speeds, the existence of artificial interstellar objects is not only plausible but arguably expected. The question isn't whether such objects could exist, the question is whether we're observing one. And to answer that question, we need more data. We need spectroscopy of the jets to determine their composition. We need precise trajectory tracking to detect any non-gravitational accelerations. We need those high-rise images from Mars to see the object's structure. We need follow-up observations as 3I Atlas continues its journey.
What we don't need is premature dismissal based on assumptions rather than evidence. For too long, the search for extraterrestrial intelligence has been confined to radio telescopes scanning for signals. We've been looking for messages, but what if the first evidence of extraterrestrial technology isn't a message? What if it's an object passing through our solar system displaying characteristics that don't quite match natural explanations? This is why the statistical improbabilities matter. They're not proof of anything, but they're a red flag that demands serious investigation rather than reflexive skepticism. Professor Lowe recently made a bet with Michael Shermer, executive director of the Skeptic Society. The bet is that within 5 years, by December 31, 2030, there will be undisputable scientific evidence for a technological artifact from an extraterrestrial civilization. The stakes might seem high, but the point is that we're now in a position where such evidence could realistically be obtained. Between the discovery of 3I Atlas, the launch of the Rubin Observatory, which will detect many more interstellar objects, and the construction of dedicated observatories by the Galileo Project, we're entering an era where systematic searches for technological signatures are becoming possible. If artifacts exist, we'll find them, and if they don't, we'll gain invaluable knowledge about the natural diversity of interstellar objects, which is also profoundly important. But we have to be willing to look. We have to be willing to ask uncomfortable questions. We have to be willing to consider possibilities that challenge our preconceptions. The 1 in 100 million odds associated with 3I Atlas don't prove it's artificial, but they do prove that it's extraordinary. And extraordinary observations demand extraordinary attention. So here's what I want you to take away from this. Science isn't about having all the answers. It's about asking the right questions. It's about following the evidence, even when it leads to unexpected places. It's about maintaining humility in the face of a vast and mysterious universe. 3I Atlas is presenting us with puzzles, the massive scale of its jets, the 7 distinct outflows appearing at perihelion, the statistical improbabilities of its mass and trajectory, the similarities to Oumuamua in terms of displaying unexpected characteristics. These puzzles might have natural explanations. They probably do, but we owe it to ourselves to investigate thoroughly, to consider all possibilities, to conduct the observations and analyses needed to truly understand what we're looking at. And if you want to follow along as this investigation continues, if you want to be part of this journey of discovery, make sure you're subscribed, hit that like button, share this video with anyone who's interested in one of the biggest mysteries currently unfolding in astronomy. Because whatever 3I Atlas turns out to be, natural or otherwise, we're witnessing something remarkable. We're gathering data about objects from beyond our solar system. We're expanding our understanding of what exists in the galaxy. We're taking the first steps toward truly exploring the interstellar realm, and that's worth paying attention to. So, where do we go from here? What happens over the next few weeks and months that will help us solve the mystery of 3I Atlas? The good news is that we're entering a prime observing period. As I mentioned earlier, 3I Atlas has moved far enough away from the Sun that Earth-based telescopes can now track it without interference from solar glare. And on December 19, 2025, it will reach its closest approach to Earth at 269 million kilometers. That might sound far, and it is by everyday standards, but in astronomical terms, it's close enough to conduct detailed observations with our most powerful instruments. Telescopes around the world are already booking observation time. Research teams are preparing their instruments. The data that comes in over the next month could be decisive. Here's what scientists are looking for. First, spectroscopy. By analyzing the light passing through the jets, we can determine their chemical composition. If we see the signatures of water vapor, carbon dioxide, carbon monoxide, and organic compounds, that supports a natural comet explanation. Comets are essentially dirty snowballs, mixtures of ice and dust, so we'd expect to see these materials. But if the spectroscopy shows something unusual, ratios of elements that don't match typical cometary composition, or compounds that are unexpected, that would be significant. It would suggest that 3I Atlas isn't a typical comet, even if it's still natural in origin. Second, velocity measurements. How fast is the material being ejected from 3I Atlas? Natural sublimation driven by solar heating produces outflow speeds of about 0.4 kilometers per second. If we're seeing speeds significantly higher than that, it would indicate a more energetic process. Chemical propulsion produces speeds of 3 to 5 kilometers per second. Ion drives can reach 10 to 50 kilometers per second. If the jets are moving faster than sublimation can explain, we need to understand why. Is there an internal heat source? Is there pressure buildup creating explosive outbursts? Or is something else generating the velocity? Third, trajectory analysis. This is perhaps the most important measurement. By tracking 3I Atlas's position with extreme precision over weeks and months, astronomers can detect even tiny deviations from a purely gravitational orbit. These non-gravitational accelerations are the smoking gun. For natural comets, we expect non-gravitational accelerations because ejected material creates a thrust like a rocket exhaust. The comet gets pushed in the direction opposite to where material is being expelled. This is well understood and well documented in cometary science. But here's the key question. Do the trajectory changes match what we'd expect from the observed outgassing, or is there a mismatch? If 3I Atlas is accelerating in ways that can't be explained by the jets we're observing, that would be extraordinary. And if those accelerations seem to be altering the trajectory, if they're correcting the orbit or changing the exit path from our solar system, that would be even more intriguing. Fourth, fragmentation searches. If 3I Atlas broke apart during perihelion, we should be able to detect separate fragments by now. They would be moving on slightly different trajectories, spreading apart over time. High-resolution imaging should reveal multiple nuclei if fragmentation occurred. If we don't see fragmentation, if the object appears to be a single, intact body, despite the enormous stresses of perihelion and the massive outflows we've observed, that tells us something about its structural integrity. Natural comets are fragile.
They break apart under stress. An object that survives what 3 Atlas has experienced would need to be unusually robust. Fifth, temporal analysis. How are the jets behaving over time? Are they fading as we'd expect from depleting volatile reserves? Are they maintaining constant intensity? Are they showing patterns that suggest controlled emission rather than passive outgassing? Natural sublimation should gradually decrease as surface ices are exhausted and as the object moves farther from the sun, receiving less solar heating. If the jets maintain intensity longer than expected, or if they shut off abruptly rather than gradually fading, those would be anomalies worth investigating. Now, beyond these immediate observations, there are longer-term opportunities to study 3 Atlas. In March 2026, NASA's Juno spacecraft will have its encounter with the object from a distance of 53 million kilometers. Juno has sensitive particle detectors that might pick up material from 3 Atlas if the jets are still active at that distance. Even if direct sampling isn't possible, Juno can gather data about the object's brightness, any remaining activity, and its trajectory. As 3I Atlas moves outward past Jupiter and beyond, there will be fewer opportunities for close observation. It will become fainter, harder to detect, gradually fading from view as it returns to the darkness of interstellar space. Eventually, it will be gone, disappearing back into the cosmic ocean from which it came. This creates a sense of urgency. We have a limited window to gather data about this remarkable visitor. Once it's gone forever. We'll never see it again. The opportunity to study an object from another star system up close is rare and precious. We can't afford to waste it. But here's something exciting to consider. 3I Atlas might not be the last interstellar visitor we study in such detail. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is scheduled to begin operations soon. This facility will conduct the most comprehensive survey of the night sky ever attempted. The Rubin Observatory will detect many more interstellar objects, objects we're currently missing because our surveys aren't sensitive enough or comprehensive enough. Some estimates suggest we might discover multiple interstellar objects every year once Rubin is fully operational. This means 3-Eye Atlas, as fascinating as it is, might be just the beginning. We might learn that interstellar visitors are more common than we realized. We might discover a whole population of objects passing through our solar system, each with its own story to tell about the distant stellar systems where they originated. And here's where it gets really interesting. The more interstellar objects we detect and study, the better our statistics become. If most of them are clearly natural comets and asteroids, showing typical characteristics and behaviors, then 3-Eye Atlas becomes even more anomalous by comparison. It would stand out as genuinely unusual. But if we discover other objects showing similar anomalies, similar statistical improbabilities, similar behaviors that challenge natural explanations, then we start to see patterns. We start to build a data set that allows for more robust conclusions. The Galileo project, led by Professor Avi Loeb, is building dedicated observatories specifically designed to detect and characterize unusual objects in our skies.
These aren't traditional astronomical telescopes. They're designed to capture high-resolution data on objects moving through our atmosphere or our near-space environment. The goal is to approach the question of extraterrestrial artifacts scientifically, not with assumptions or preconceptions, but with instruments and methods capable of gathering definitive data. If technological objects are visiting our solar system, whether from other civilizations or our own future missions that have returned, we should be able to detect and identify them. This represents a fundamental shift in how we think about the search for extraterrestrial intelligence. For decades, SETI has focused on radio signals, looking for messages from distant stars. But what if the first evidence isn't a message? What if it's a physical object we can observe, track, and potentially even approach? The technology needed to detect interstellar spacecraft isn't exotic. It's essentially the same technology we use to study comets, asteroids, and other solar system objects. We just need to apply it systematically and be willing to follow the evidence wherever it leads. Why does this matter? If 3-Eye Atlas is natural, we're learning that interstellar comets are far more massive and active than predicted, expanding our understanding of the galaxy's material. That's valuable knowledge. But if it's artificial, that would be the most significant discovery in human history. It would prove we're not alone, that interstellar travel is possible, and that other civilizations existed or existed. The philosophical and scientific implications would be staggering, fundamentally changing how we see ourselves and our future. Even the possibility deserves serious investigation. Scientists like Avi Loeb are pushing for systematic searches, not because they're convinced, but because the question is important enough and the public is ready. Look at the interest in 3-Eye Atlas. There's a hunger for knowledge about our place in the universe. We've talked about the impossible jets stretching millions of kilometers, the 7 distinct outflows that appeared at Perihelion, the 1 in 100 million odds behind its trajectory, and the unexplained data gaps from Mars. These aren't wild guesses or sci-fi fantasies. These are real scientific anomalies demanding real answers. So stay curious, stay alert, and never assume the universe must fit our expectations just because the truth feels uncomfortable. 3-Eye Atlas is out there right now, moving through our solar system in real time. Every new observation adds another piece to a puzzle we've never seen before. This is science happening in front of our eyes, and you're part of it simply by paying attention, learning, and asking the right questions. By following these discoveries and thinking critically, you're participating in humanity's oldest mission, understanding where we came from, what's out there, and whether we're truly alone. So make sure you subscribe to follow the unfolding story of 3-Eye Atlas and other interstellar visitors. Hit the notification bell so you don't miss the next update. Drop a comment with your theories. Share this video with anyone who loves space, mysteries, or the thrill of the unknown. And if you want deeper scientific analysis, read Professor Avi Loeb's latest papers. They shed light on just how unusual this object really is. The next few weeks are absolutely crucial.
December 19th marks its closest approach to Earth. New spectroscopic data is being analyzed as we speak. Trajectory measurements may confirm non-gravitational acceleration, and high-resolution imaging will soon reveal details we've never seen before. Piece by piece, the picture is coming together, but the story is still being written, and the most important chapters may lie just ahead. Whatever we discover, one thing is certain: this object is teaching us something profound about the universe and possibly about ourselves. Thank you for being part of this journey through one of the most mysterious discoveries of our time. Keep looking up. Keep questioning everything. 3i Atlas may be about to show us that the universe is stranger and far more fascinating than we ever imagined. Make sure you're subscribed, hit that like button, and I'll see you in the next update. Stay curious and keep exploring the cosmos.